let's say we have some function or some curve and we're trying to calculate the area underneath it. And so what you might do, or what you might consider to do, is by adding a bunch of rectangles underneath that hit the curve at some point, and then you go along some width, and then you calculate the area of that triangle, and then you do that a whole bunch of times, and then you see what that total area is going to equal. Okay, and what you might notice if you go on that train of thought is that if you take the width of those rectangles to 0, what you'll notice is that you'll have an infinite number of rectangles under the curve to calculate. So that's not really ideal if you're trying to calculate it by hand. But your observation would be that, hey, if I take the number of rectangles to infinity under a curve, I will calculate the exact area. So you might be getting an intuitive feel for, if I want to calculate the area under a curve, I need to start calculating the area of rectangles and just adding them all together. So you're just summing a bunch of rectangles. And so we're going to go ahead and do that here for one example. And so there's actually nothing particularly fancy about rectangles other than the fact that the area is simple to calculate. It's just length times width. Okay, if you wanted to get a nice approximation under a curve, you could use the area of a trapezium. However, regardless of whether you're using rectangles or trapeziums, as you take the number of objects, so rectangles or trapeziums, underneath the curve to infinity, so you make their width 0, you get an exact answer for the area under the curve. So that's an important notation there. But for the case of being intuitively correct when it comes to understanding this with the fundamental theorem of calculus, it's probably best to just stick to thinking of area under curve as just adding a bunch of rectangles together. So we've got one here on the screen. I'm just going to zoom through and calculate the area because here we can see that, I'll do this in red. Here we can see we're going to have some error. Okay, we're missing out. All of this red could be potential area to add, and so there's going to be some error. So our calculation is not going to be exact. And the way we would add it is we'd say the length here, this blue length, I would say that has got a length equal to f of x. Okay, where x in this case is 1. So if I was calculating the length of that rectangle, I'd say it's f of 1. And the width here, I would say that the width is equal just to 1 there. Alright, now I'm going to go ahead and calculate the area of that rectangle there, and I'm going to do that for all 5. Okay, and so here we can see, well, if we did that for all 5 rectangles, we'd get an area of 10.5 units squared. Now, there's obviously going to be a little bit of, that's a little bit of an underestimation. Okay, it might be closer to, I don't know, maybe 11 units squared, because here we can see in this red that there is going to be some missed area calculation between 1 and 6 there, between these 2 points. So we're off by a little bit of an approximation. Okay, but if we wanted to get a better approximation of the area, what we could do is we could just consider 10 rectangles between 1 and 6. What we'd have here is we'd have the length is equal to the same thing. It's just going to be f of whatever that x point is. So at least for here, it would be f of 1.5. And in this case here, the width would be equal to 0.5 because we've made the width smaller. Okay, but I'm not going to calculate the area for 10 rectangles simply because I cannot be bothered, because calculating it for 5 was enough. And so you might think, well, imagine doing this for an infinite amount of rectangles. That would not really be fun. Surely there is a nice way to do this. And it turns out there is. And this is where our integral notation comes in. All right, and it's not precisely correct, but it really helps us get a good feel. So this is why when we take our integral sign and we take the integral of a function, f of x, and we tag on this dx, all right, this is really what the notation's saying. All right, this integral sign is like a big S. And it's a big S because it stands for summing a bunch of stuff. Okay, because it's just going to sum a bunch of rectangles, where f of x here, where f of x here is just going to be the length of each rectangle. So that's going to be the length at every x point, And then this corresponding dx here, this corresponding dx is, actually let me do this in a different color. Let me do this in a red. Let me do it in a red. This corresponding dx here is going to be that little nudge along. That little nudge. And that little nudge is the width. So when we are reading this integral notation, I think it is healthy to read it as summing a bunch of rectangles where the length of the rectangle is f of x and the width is d of x. Okay, that's how you want to intuitively read that. So I'm going to put it in a sentence. Okay, where that width of dx is just that little nudge or that little push in the x direction. Okay, and so this is the integral notation, and I really do think it is healthy to read the integral notation as just calculating the area under a curve. Now, how taking an antiderivative lies in this has really got to do with the fundamental theorem of calculus, which relates slopes and areas between functions. Right, but just to get a feel for estimating areas under a curve, this is a good strategy to use.